Hi guys, this is PHYZ Universal, and today I'm going to show you how can you derive the formula, find the speed of electrons or the derivative velocity of electrons in a conductor. um, yes, before I start, I know that most of you are just asking themselves some questions. What could be the speed of electricity? You know that when you switch on the switch, sometimes you see the light goes on incredibly fast. In a second, you just see the last one. So you never know what speed the idea behind. But today, in this video, I'm going to show how can you find the exact formula that you can use and you can determine the speed of electricity, and I'm going to explain it step by step. So now I'll go step by step and let's begin. And before that, you should know that you can subscribe and comment or like. You can even share with your friends, your colleagues, so that they can get new ideas, they can explore the world, because you know that you study science in order to explore nature, the world, because the world is governed by different sets of formulas of which you have to find out. So now I'm going to show you different formula that you can use, and this formula to find the speed of electrons or the derivative velocity of electrons in a conductor. So now let's go together. So to start off, we're going to start with the volume of this conductor, and here guys some different variables that we're probably going to need in case of deriving this formula. So we're going to need E. This is elementary charge, and it's values to 1.6 times 10 raised to the power of negative 19 coulomb per electrons. But guys, you may wonder, I have not put per electrons, but for the matter of simplicity, just write it coulomb, only that. But you know that just the quantum charge carried by single electrons, and yes, the discrete number, okay, doesn't exist there. So we're going to need V. This is the volume of the conductor, very simple to understand. We're going to have L, this as the length of a conductor, and Vd, this is the derivative velocity of electrons of which we are looking for, and Q, this is the quantum of charges flowing in this conductor, and N, this is the number of electrons per unit volume of this conductor. Having told you these variables, now let's begin by the volume of this conductor. So the volume of this conductor is given by the area or the cross-section area. In this case, I'm talking about the cross-section area, because this is the cylindrical conductor. The cross-section area you multiply by the length. What do I mean? I mean this cross-section area and this length from here to that point. So this will be the volume of this conductor. uh, Having seen the volume, now we know that N, this is the number of electrons per unit volume. So having this volume, we can now go ahead that the number of electrons, let's treat as E bar to bar, so that I can just differentiate from the E which we are talking about. So the number of electrons per unit volume is given by N, you multiply by the area, you multiply by the length. So this will be the number of electrons per unit volume now. So since the electrons are just flowing, you know that electrons carries negative charges. That's known from the elementary study, and the quantity of electricity flowing in this conductor is given by the number of electrons you multiply by the elementary charge. This is E. So this is the formula for calculating the quantity of charges flowing in this conductor. So now we can just go ahead. We say the quantity of charges flowing is given by N, you multiply by the area, the length, and E. So this will be the quantity of charges flowing in this conductor. So since there is the current flowing this conductor, and the current, you know that this the quantity of charges flowing per unit volume, per unit time, well, I'm sorry, per unit time, is the quantity of charges flowing per unit time. Therefore, at a certain point, at a certain point, let's say from this point to this point per unit time, so that quantity of charge which are passed at that time interval, that's be the current. So the current the current is represented as I, just like as I is equal to the quantity of charges flowing at a point per unit time, or in this case you can just say the rate of flow of charges. Okay, so this will be the current. So the current now in this case is given by Q over T. So Q is N times A times L, then you multiply by E, you divide by time. So this will be the current in general flowing in that conductor. But guys, I'd like you to focus on this thing, L over T. In physics, when you take the, the distance between 2 points over the time interval, this will be the speed, okay, which is in meter and the time is in seconds. So that's in meters per second. This the SI unit of velocity. By this speed, the speed which we're talking about is just Vd, or the derivative velocity of uh, these electrons in a conductor. So we can just go ahead and substitute Vd in this equation. So I is basically N times A times Vd times E. So now you can see that the formula is now being simplified at a time. So we can just make Vd the subject since this is what you're interested in. So Vd is nothing like 1 I over N times A times E. So this is the derivative velocity of electrons, and this is just the formula that you can use. So as you know that in physics, whenever you are driving anything, you have to make sure that the units are correct. Okay, you put everything in its SI units, in the SI unit order, and you must make sure that they're in the exact SI unit so that you can't mess up anyhow. So now let's prove that actual Vd is in meters per second. So Vd is given by, the current is the quantity of charges flowing per second, or this coulomb per second. You multiply by n. N, guys, as I defined before, is n is in electrons per unit volume, so the number of electrons per unit volume. So in this case, you're going to have 1 over n per cubic meters. Then you multiply by the area. The area is 1 over meter square, and then you multiply by E. This is coulomb per electrons, so 1 over coulomb per electrons, which is just represented by n. So now we can just simplify all the stuffs. This coulomb per second, you multiply by cubic meters per n, you multiply by 1 over square meter, you multiply by n over coulomb. So now you can see that these stuffs, C and coulomb, yes, go that, and n will go. So cubic meter over cubic square, or meter square, yes, meter. So we're basically going to remain with m on top and seconds at the bottom. So this is meters per second. So now you can see that this actually formula is correct because it gives exact units. So now guys, this is the way you can just calculate the speed or the derivative velocity of electrons in a conductor, and this derivative velocity is extremely small, and you just realize you can just plug in the values of current, the number of electrons, the area, and the momentary charge. You'll find that this value is very tiny. And What can you do now? What can you explain about that? The electrons move extremely slow, very slow. You can't imagine. Yes, even the scenario itself, according to the findings, the snare moves just faster than electrons. You can't imagine. But you find that the electrons move extremely fast. And what could be the reason now with that speed? You know that electrons, uh, they have their own electric field. So that electric field just push them away incredibly fast, and you can just demonstrate this uh, by having the student in the class, many students in the class in the large room, or and then when you ring the bell, not all the students will go out at a time. Maybe actually the person or the student who is uh, just next to the door will actually go out at the instant they get that bell, the sound of the bell, or the sound of the bell just from there. So now that's the sound of bell. That's the first thing that the student at next to the door will hear, and then you get out. But others will be squeezing in on the door, others will just fall down. So now that's exactly the way the electrons move. So that sound of the bell now is the effect now that pushes the electrons, and that's the anode or the electron